Light. Without light, even the simplest kind of orientation and communication may prove most difficult. Today, we are to a large extent capable of controlling light, and we can use it as a technological means of communication. We feel an increasing urge to be in contact with each other, and by means of the new optical technologies, light will be playing a still more decisive role in our lives in the future. For a long time, electricity has been the all-important technology, enabling us to communicate. Electricity is movement of electrons that may seem lightweight, but are physically heavy, which means that they are moving slowly. On the other hand, communication by light is movement of photons, which are massless and able to move considerably faster. Consequently, solutions with light as means of communication, the so-called optical communication, will be much faster than the electronic communication. We are on the threshold of a new generation of technology. DTU Photonics is an education and research institute of international format, located at the Technical University of Denmark. Researchers here are at the cutting edge of the technological development within optical communication. Laser light plays a decisive role. The invention of the laser is by far one of the greatest achievements of the 20th century. Since its invention in 1960, research in laser applications has resulted in no less than 13 Nobel Prizes. Most of us are in contact with laser technology every day. The introduction of laser as a means of communication has changed the world fundamentally. The laser blazed the trail for the internet, which has turned our ways of communication upside down. By a single click, we can now download enormous amounts of information onto our own computers at lightning speed. Internet traffic is increasing by about 60% a year, so the demand for much faster data transmission is strong. At DTU Photonics, research is therefore persistently going on, with a view to finding solutions to the communication systems of the future. During the infancy of electricity, it was barely managed by means of heavy copper wires and a considerable number of telephone operators to keep a few hundred lines operational. Today, large parts of the electronic communication systems have been replaced by optical fibers. Light forms the basis of the broadband network that we all use when we're watching television, speaking on the phone, or surfing on the internet. Our globe is actually entangled in optical fibers containing laser light, fibers which connect all continents, countries, and towns. The name World Wide Web has never been more descriptive. An optical fiber can contain about 25 quadrillion light impulses per second, or well over 250,000 times more than an electric cable, which is not even able to transmit very far. In an optical communication system, laser light carries the information at lightning speed in the shape of light impulses. It is equivalent to the ones and zeros of the computer language. Optical communication is, however, still dependent on electronics, because the information is transmitted and received as electronic signals. It's only on its way from one computer to the other that the information appears as light impulses. The researchers at the laboratory are among the best in the world when it comes to transforming and packing enormous amounts of electronic data onto a single light wavelength. The challenge is not least to be able to retransform the light to electronic impulses. enabling electronic apparatuses like computers to keep up again. The light signals are called bits. Data transmission of 640 gigabits or 640 billion bits per second is the world record, and DTU Photonics were the first in Europe to attain this bit speed, which is equivalent to being able to transfer all telephone conversations in Germany, France, Italy and England at the same time through one single optical fiber. Arrangement of bits in this way is very useful when large amounts of data are to be transferred at a really high speed. Theoretically, a single optical fiber is capable of carrying all the traffic on the internet. The challenge is how to transmit so much information at the same time, since electronics cannot keep up at all. In order to cover the future demand for data transfer, we have to replace electronics with purely optical technologies, due to the fact that as long as the fast optical components have to cooperate with the slower electronic components, the data speed will be limited and create a bottleneck.
What goes into it? Where do we get it? How much does it cost?
Optics is presently going through a development which is similar to that of electronics in the 1960s. Here, so-called integrated circuits made electronics take up less space, so that a number of electronic apparatuses could become a natural part of everyday life. In the clean room at DTU, they're working on improving the components, transforming the signals from electrical to optical and back. The optical chip, which will replace the electronic chip in the future, are called photonic integrated circuits. Optical chips combine many tiny lasers. Each individual laser transmits information on a certain color of the light. It means that a laser of one color can transmit one kind of information, while a laser of another color transmits a different kind. In this way, all communication can take place through one and the same fiber. These superchips are today on their way to mass production. The research in optical chips is rich in interesting perspectives. When it becomes possible to extend the amount of information that can be transmitted through optical fibers, the consumers will obtain faster internet connections. But the dream among researchers is that sometime in the not-too-distant future, we shall also be able to transmit and receive 3D television or play 3D video games in our own homes. The researchers' capabilities of steering light have also contributed to technological development in other areas. A group of researchers at DTU Photonics can, for instance, determine the chemical properties of various substances exclusively by trans-illuminating them with an ultra-high frequency light pulse. The principle behind the measuring is comparable with radar. A very short light impulse is sent towards the liquid, and the reverberated echo from the liquid contains information about the contents and can tell, for example, whether it's inflammable or contains undesirable substances. In the future, this so-called terahertz technology will, among other things, be useful at airport security checkpoints, where transillumination of materials quickly will make it possible to ascertain whether they are dangerous. This technology will also be applicable within food control. The amount and quality of water in foodstuffs is supremely important to the quality and shelf life of the product. Even the space industry is very interested in terahertz technology, as the beams can be used for transillumination of rocket insulation. The technology might, for instance, have prevented the loss of the space shuttle Columbia back in 2003, where a loose piece of insulation was the cause of the catastrophe. Communication and measuring techniques of the future are based on one of the most elementary things in the world, light. By understanding its nature better and subsequently steering it, brand new possibilities begin to emerge. The optical horizons are painting a future of more and faster communication, which is likely to spread to more areas of everyday life. Light has always brought people in contact with each other, but in the future, contact may be made through whole new channels.